Hello and welcome everybody. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be sitting alongside your host, Steve Dodds. In this particular webinar, we'll take a closer look at some basic OptiBPM examples. During the presentation, we will have two question and answer periods, the first one approximately 20 minutes in, and the second at the very end. During the presentation, I will launch 3 polls such as the one you're looking at now. Each of these polls is very important to us as they provide Steve with useful information for guiding the presentation. Please also note that this webinar will be recorded and distributed to everybody that registered. You will receive an email tomorrow at 2 p.m. Eastern Standard Time, so 1 hour from now tomorrow. It's now time to get the presentation started, so I'll hand it over to your presenter, our OptiBPM product manager, Steve Dodds.
Thank you, Brian. Welcome to the second webinar on OptiBPM. OptiBPM is a software that permits the simulation of optical propagation on optical waveguides and optical fibers by the beam propagation method. Today, I would like to show an example of a typical design session and to look at a component that is popular and which sometimes confuses people the first time they see it. It has some surprising properties. The question today is, can we take optical power from 2 waveguides and combine all of the power onto a single waveguide? Or could we take optical power from 2 optical fibers and combine it onto a single optical fiber? And the answer is yes, sometimes under specific conditions. And the beam propagation method is a good way to observe these details. So I spent a little while trying a little design, and I drew some waveguides in a layout, 2 waveguides that approach each other and come to a single waveguide. In 3 dimensions, my design looks something like this. Maybe it doesn't surprise too much to learn that this one actually can combine optical power successfully. In OptiBPM, we need to specify the optical field at the initial point of excitation, which is here, the plane represented by the red line in the layout. If we go into this dialog box, we can see the details of this excitation. On the right-hand panel is a list of all of the waveguides that cross the input plane. And on the left panel are which of those waveguides were selected for input. In this case, they both are. And they are selected to have the same amplitude. So when this simulation begins, it will find the optical mode to be found on the waveguide on the left. I'm looking at the transverse XY plane now. It will find the optical mode to be found on the right, and it will use these two modes added together for the initial excitation to simulate the condition of light coming from both waveguides and approaching each other to a single waveguide. So we'll begin the beam propagation method simulator now. We can view this in a number of different ways. Let's look at the propagation plane. So there's the light approaching and the two waveguides together. And it does appear that the optical power is getting greater. Let's go to the analyzer for a more detailed look. And there's our result. And let's have a closer look at this. This plot occurs at the position that you see the red line on the right. I'm going to do a little bit of magic with the axes in this case because the view is not very clear if you set the range automatically. We'll get a clearer view of what's going on if we fix the scales to be exactly 1 and 2. So at the excitation we have light in two waveguides, and the amplitude of the electric field is 1 in both cases. We can assume that the power has been normalized so that an amplitude of 1 meant unit power. And what happens? We move through the simulation and the light comes together and, oh yes, it becomes something like 1. Where does it go? Well, let's have a look. There is a tracing feature here so we can see precisely what the levels are. So at this point it reached an amplitude of 1.4. Well, that's the amplitude of the field, and assuming that the normalization of power is going to be the square of this, 1.4 squared, yes, it is close to 2. So we can expect that this did mean that all of the power in the input, that the unit power on the left, the unit power on the right, that when it came together, the amplitude now being 1.4 means that, yes, most of the power was combined together. When we do a BPM simulation, it's a good idea to observe the phase of the envelope as well as the amplitude. And when we do that, we can see that, yes, the phase is starting at 0 in the two waveguides and they come together. And there's not too much change in the phase during the propagation, which means that the reference index was set properly. So this is a good BPM simulation. But looking at the phase, this is a clue to something that might influence things. The optical phase of both waveguides at the excitation point, at the entry point, it's 0, both of them. And when the two waves come together, they still have nearly 0 phase. So that might beg the question, what happens if they're not the same phase? So let's investigate that by looking at another sample. And in BPM, we can adjust not just the amplitude of the two waves, but we can also adjust the phase. So let's look at the waveguide that's at the lower point is the first one. Let's look at this, and it's got amplitude 1 and phase of 0. Well, let's set this one to the opposite phase, a phase of pi. A phase of pi is 180 degrees. So let's set it that way. So now we've got, in our next simulation, we're going to have two waves of unit amplitude, but opposite phase. Let's have a look what happens now. And we'll go to the propagation view. There are the waves, and they come together. They get closer and closer. And what happens? Oh, they seem to be avoiding each other. Well, they don't like each other anymore now that they have opposite phase. Yeah, let's look at what happened this time. What happened? Well, let's look at the power in the output waveguides. Oh, it looks like 0. And yes, indeed, it's something so small that it was using scientific notation to describe its size, 10 to the minus 7. Very small. Okay, so no power was transmitted in this case. And let's have a look. That's what the amplitude looked like. Let's look at the phase. Yeah, there it is. So from this picture, it's fairly obvious what happened. Here is a phase of 0. And on the other waveguide, we've got red and we've got blue. But you see, red is pi, blue is minus pi, and we know that minus pi is the same thing as pi in phase space. So it doesn't matter if it's blue or red, it's the same phase, and it's the opposite of green. And so no, they don't come together. It's even more instructive if you look at the real part of the envelope function. The real part is positive on the upper waveguide, and because it's the opposite phase in the lower waveguide, it's negative. And so plus and minus, no, they don't mix very well. Once again, I'm going to adjust the axis to be not auto range, because you really do need to see the absolute values when these things come together. The relatives don't make much sense. So let's fix the scope here. And when we move together, let me arrange my windows a little bit so you can see things. When we move together, the waves, they come together, and well, not too surprisingly, they cancel each other out, don't they? And then they've canceled each other out, but then the energy is still there, so it has to radiate away, and now we see a radiation pattern forming after the junction. Yeah, so we can combine light from two waveguides, but it does depend on the specific input conditions. But we did see that, let me bring up the, let's have a look at our first simulation again. I can have a look at the first simulation, by using the OptiBPM analyzer. That's a dedicated application that simply looks at all of the simulations that we've saved so far, just looks at the results. So the first one we did was that one. And when the amplitudes were equal and in phase, we got combining with almost no power loss. And we found that if the phases aren't the same, that then we get zero transmission. Maybe that's not too surprising. But here's something that often catches people off guard the first time they see this. They see this picture, they say, oh, this is a lossless combiner when we have two inputs. And then they're surprised that if you turn off one of these waveguides, if one of these waveguides goes dark, the combiner isn't lossless anymore. That's a little bit surprising the first time you see this. If you haven't seen it before, let me show it to you now. We're going to go to the input plane, and we're going to look at our input fields. And we're going to just get rid of one of them. We aren't going to have any optical propagation in the lower waveguide. We're going to remove it. So now we're going to have optical excitation only on the upper waveguide. So we have this this picture on the right of lossless combiner in our minds, and we say, okay, one of these excitations went dark, and you don't expect any trouble, but what happens? Okay, there's our light coming in from the upper waveguide. So far, so good. But, oh, something strange is happening, and it sort of looks like there wasn't as much power going out as there was coming in. And let's have a closer look at this. We'll bring up our viewer, and once again I will adjust the axes so that you get a fixed view. The auto range is not very informative. So there's our amplitude of 1 at the input, and we proceed. We approach the junction. Something funny happens. And when we come out the other side, it doesn't appear to be full power anymore. Let's have a closer look. And we get about 0.7, about 0.7, 0.7 squared. It's about a half. And then we look at the power and output waveguides report from OptiBPM, and it confirms it, 49%. So this was a lossless coupler when we had both waveguides lit equally, but when one of them turned off, the remaining one suddenly became lossy. And the first time people see this, they think, aha, there must be something wrong with this design. Surely if I change things somehow, I must be able to make it so that it's lossless in both cases. Well, that's not the case. And it's actually fairly easy to prove this with a simple theoretical analysis. And I'm going to show that to you now. But before doing that, I'm going to take a little break, give us a chance to look at some of your questions, and give Brian a chance to ask you some question. He's going to launch a poll to ask you a few questions. All right, I'll see you in a few minutes after the poll.
Okay, thanks,
Over to
Steve.
you, Brian.
Okay, so as many of you have seen in previous sessions, same type of polls. Again, we're just using this to determine our audience and determine how to better the webinar content in the future. So your participation is always appreciated. Let me just check the BPM schedule for the next couple of days for you guys. Tomorrow we have, actually not tomorrow, on Friday we have our last BPM session, it looks like, and that will be at 1 p.m. Eastern Standard Time. So it's going to be on advanced applications. You can go to the website and click on the first banner that you see, which will take you to the webinar week. Or you can just wait for about 15 minutes. I'll go ahead and throw the link in the chat window. I'm not sure if you guys have the chat window open and you're seeing some of the stuff that I'm putting in there, but I'll go ahead and throw some information and links during Steve's second session, just to help you guys get organized a little quicker if you want to attend additional sessions, or if you're interested in looking at the recorded videos of other sessions, or maybe the first BPM session, and or check the $50 winner of the draw that we'll have announced in about 40 minutes from now. So I'm going to go ahead and close the poll now, pass it back to Steve. If you haven't had a chance to get a question submitted, we'll have one more Q&A period at the end, so maybe 20 minutes from now. So please go ahead and formulate those questions and get them in. We'd like to answer as many as we can right now while we have one-on-one communication with you guys. So I'll pass it off to you now, Steve.
Thank you, Brian. So we were left with a perplexing situation that when there was light on both channels, they combine, but when they're without loss, and when there's light on only one channel, suddenly we seem to lose half the power. And how could this be? Well, as promised, this is actually fairly easy to predict by quite simple fundamental arguments. You don't even really need any math. It comes out just from basic properties. We can start with just a simple block diagram to represent the situation. We have a space where there's some electromagnetic fields, and we have two inputs labeled 1 and 2. Amplitude A1, amplitude A2. By amplitude, I mean the amplitude of the electric field or the amplitude of the magnetic field. And so we've got two amplitudes going in. We have one amplitude coming out. And we assume that these are normalized, these amplitudes are normalized such that when you square the amplitude, you get the power. And that's what's going on the right-hand side. We've got A1 squared in and A1 squared 2 in to get A squared out. So that's what's going on. And in the first simulation, we put unit amplitude in port 1. In the last simulation, we put unit amplitude in port 1 and nothing in port 2. And Without loss of generality, we can say that the output was T, where T is at the moment an unknown, T for transmission. And T would represent an amplitude, so T would represent either an electric field or a magnetic field. And 1 represents setting the electric field or the magnetic field to 1, and 0, no field. And on the power side of things, everything is just squared. So there's unit power going in port 1, no power going in port 2. And if that's true, then the power out must be T squared, or, well, more precisely, the modulus T squared. And this was a symmetric coupler. So if I had arranged unit amplitude to go into port 1 and I got T out, I must get the same thing if I put unit amplitude in port 2 and nothing in port 1, like that. You have to get the same T. And of course, the power that comes out is the same T squared. So in the next slide, we do have to use a little bit of physics. And the physical observation is that Maxwell's equations are linear in the fields. They're linear in electric fields. They're linear in magnetic fields. They are not linear in power, because power is always, well, power is E cross H, or it's E squared or H squared. It's always a quadratic. So no, Maxwell's equations are definitely not linear in power. And the reason why the linearity is important is because if I imagine inside the box an electromagnetic field, and it was that electromagnetic field that results when the excitation is, as shown, 1 on the top, 0 on the bottom, I get an electromagnetic field out, and it so happens the amplitude of that is T. This will, the second, if putting the excitation in port 2 will yield a different electromagnetic field. And it so happens, because it's symmetric, that I got the same transmission out. But because they're linear, if I now, in the next step, if I put field in both ports, I can find what the electromagnetic field is inside the box by simply taking the arithmetic sum of E1 and E2, electric field 1, electric field 2, or magnetic field 1 and magnetic field 2, and that applies to the transmission coefficient. So when I put unit amplitude in both ports, the transmission will come out to be 2 times T. It's going to be T plus T. Why? Because Maxwell's equations are linear. If I want to find out what happens to the power, I have to take the square of this. So 1 squared is 1 and 1, and 2T squared is 4T squared. And we already know that in this configuration, our combiner is lossless. So we know that when we put 1 unit of power in on both ports, we get 2 units of power out. We've already seen that. So because of that, we know that 4T squared must be 2. All right, there's a little bit of math. 4T squared equals 2. You do the math and you find out that T is 1 over the square root of 2. Okay, there's the math. It's done. It's over. So this works well when we've got the both inputs on, but oh yeah, so in here I've just taken the T and plugged it in. So with both inputs on, we got 2t on the outside, which is root 2, and we did observe an amplitude of the square root of 2 when we had the two inputs on. And with a power equal both sides, we did get to 4t squared, we got a power of 2 out. So everything looks kosher. So let's go back to what happens when one of the amplitudes goes dark. Well, now we know what the t is. When we've got 1 and 0, we know that the transmission was t. That's what we first, that was what was in our first slide. And now we know that t is 1 over root 2. To find out what the power is for that, it's t squared, a half. So in this configuration, the power in is 1, but the power out is a half. And it doesn't seem to be much we can do about that. It's going to be like that no matter what we do. You might be wondering now, how could that be possible? How is it that when you have light on only one arm, what's going on? Well, if you look carefully here, you can see something that appears like an interference pattern, and there does appear to be some kind of radiation coming out here. Let's go to a different view of the data, and there you can see the interference pattern, and this is elevated above 0, which means that, yeah, there is indeed light being radiated away. So you have unit power coming in and only half of it being transmitted. What happens to the other half? It gets radiated away. Yeah. It's a little bit mysterious. And so maybe we can see, we can also look at it from this view as well. Trace through. I'll set the automatic range to so that you can watch how the amplitude changes as we move. So everything is fine. We're moving towards the junction. There's some kind of interference pattern that occurs. And then after that, you can see, oh yes, there's some kind of radiation occurring here. Light is leaving the simulation boundaries. The simulation boundaries have transparent boundaries at the end, so if light approaches the boundary, it actually leaves the simulation. There is another metric that shows that this is the relative power. This shows the power in the cross-section plane as a function of propagation. And yes, indeed, that is what's happening. Let's trace this one too. Information trace. So at the beginning, there is unit power in the simulation window, and it's keeping more or less there. But after getting towards the end of the simulation, we see that the total power in the simulation seems to be going down. And yes, it does go down to about almost a half. At the end of our simulation, there's still a little bit of optical power left outside of the mode. Oops, wrong picture. This picture. There's still a little bit of optical power left outside here. But it is amazing that how Mother Nature knows how to obey her own laws. She knows that by the time we get to the end of the simulation, we must lose half the power. How does she arrange it? Some kind of weird interference pattern you never could have guessed. I don't know how she does it, but she does it. It's amazing. And there's no point in trying to get past this. You can prove it's a basic physical property. Trying to make it lossless in the single arm excitation case is a little bit like trying to design a perpetual motion machine. There are good physical laws that will forbid it. Anyway, hoped you found that entertaining. That's all I mean to say to you today. And if you have any questions about this or want to see in more detail, you can just send us along an email to support@optiwave.com, and I will respond. Goodbye for now. Back to you, Brian.
Okay, so we'll go ahead and throw up the last poll here. It's your last chance to ask your questions if you have any, guys. Please do so now. I believe the any questions that haven't been answered this session will respond directly afterwards. If there's any new ones that come in this last couple seconds, I believe Steve will go ahead and answer those. And I'll just give it another 10 or so seconds if you have an urgent question. Otherwise, if you guys have anything else afterwards, 2 email addresses to get a hold of us for pretty much everything. Info@optiwave.com for anything evaluation related or quotation related. Otherwise, technical support, technical questions, or just anything in regards to the software products themselves, you can email support@optiwave.com. That goes out to pretty much the entire team, and we just divvy up the work appropriately depending on which topic it is. So anything BPM related, if you send it to support@optiwave.com, Steve will get it. Okay, I'll go ahead and close the last poll here. There were no questions that came up. Actually, one just came up right now. I'll have Steve take a really quick look at it and see if he wants to reply to that.
Hello. Yes, we do have a question. My old friend Anatoly wants to know if an MMI coupler can be lossless. And well, Anatoly, I haven't tried it, but I am quite convinced that we will get similar properties to what we've just witnessed, because I'm sure the theoretical analysis of MMI applies that analysis. Well, it would apply whether we have MMI in the box or if we have something else. I haven't tried it, but I'll be quite surprised to find if there's any fundamental difference. Okay, hearing no other questions, I think it's time to say goodbye. Thank you all for attending, and maybe we'll see you all again sometime soon. Bye for now.